Well, let's dig right into your research. So you sit at the intersection of delivery logistics and machine learning. Do you want to tell us a bit about why that's interesting? And I also know you have a lot of association with the business analytics program. You have an operations research background. So maybe you can tie those different fields together.
Yeah, sure. So, my first job out of college, I was an intern at Schneider Logistics, which was a subsidiary of Schneider Trucking. So if you've seen the orange trucks on the road, that's Schneider, and they're based in my hometown of Green Bay, Wisconsin. So I ended up there in an internship. So kind of found my way into the trucking business. And, one of the things that we were doing at that time, it was kind of the dawn of third-party logistics. So we were working with, a lot of different clients, helping them, in many cases, move different components to manufacturing facilities. And, one of the things that happens in that context is that, you don't necessarily fill up a full truckload. And so we were looking at ways of improving the cost by, along the way, stopping somewhere else and putting more in the truck to get, better, essentially, utilization. And so that led me into kind of a career in logistics and particularly vehicle routing, and eventually to a PhD program in operations research where, we were exploring these problems as part of a Sloan Industry Foundation program at that time. So I come to these as an operations researcher, as somebody trying to optimize. And so first and foremost, that's kind of the lens that I take to these problems, and only came to the machine learning side much later. So a lot of the early work that I did in these applications, we were trying to certainly solve problems, essentially, find policies for the decision making. But we were incredibly limited at that time. And the class of problems that I was working on are called sequential decision problems. Mm-hmm. And so essentially, we're going to make a decision now. We'll incur a cost. We'll receive some sort of reward. And that will have, though, an impact on the future. But at the same time, of course, the future is unknown. So we're making this decision, and we're going to make another decision in an unknown future. But by making this current decision will affect perhaps the decisions that are available to us in the future. And so you model those as Markov decision processes. And a Markov decision process, or an MDP, is well known to have the curses of dimensionality. And the traditional method of solving these, at least a finite horizon problem, is to use what's called backward dynamic programming. But what that means I need to be able to do is I need to essentially enumerate the different paths in this problem. And so these curses of dimensionality come into play, and the one that's most famous is what we call the state space, the curse of state space dimensionality, is that I can't possibly, in most cases, write out every possible future state that I could find myself in based on every possible decision that I could make along the way. And so we really, particularly in the late 90s, that reduced a lot of, if we wanted to solve it exactly, that reduced us to very toy problems. And in logistics, that meant maybe I could take a small road network and, with some very, limited stochastic outcomes, and we could solve these small problems. So what we spent a lot of our time doing at that time was trying to understand kind of the mathematical structure of the optimal solution. And, this has been incredibly powerful in things like inventory control. The the structure didn't, it wasn't as evident, unfortunately, when you get into the vehicle routing problems. This dimension of time and space that you have in routing often made that difficult. And so, from there, we sort of turned to a lot of kind of heuristic decision making. And the easiest thing to do is simply to ignore the future when you make your decision right now. And we call that a myopic decision making. And, it's easy to show example after example where that puts you into really bad positions in terms of the future decision making. And so the goal in a lot of the work then that I was doing was how do we solve something using a heuristic that has at least some accounting for the future? And that kind of became a big part of my research. Then, though, we kind of have the reemergence of machine learning, particularly the advent of deep learning, and you realize now that we can approximate the future through the neural net as that approximation architecture, and we wipe away the problem of the state space. And so that has, for the last, 10 years, that has sort of been just an amazing advance, I think, for the kind of work that I do. The challenge, though, is that there are still other curses of dimensionality. And when you're dealing with a routing problem, that can be the combinatorics of the solutions. So some of you may be familiar with the traveling salesperson problem, where I have, let's say, a set of cities, and I want to build a path, right, that visits all those cities, and maybe, technically I want to return to the starting point. And, if you think about that as the number of cities is growing, right, the number of different ways in which I can order that is exploding. And of course, there has been an incredible amount of work on this. Many of you may know Bill Cook and his Concord solver, and they can solve just incredibly large.
Tell us about that. I don't know about that.
Problems. So, so this is, this goes back to, I don't even know how long, right? The Königsberg Bridge problem, and it has similarities to this and traveling salesperson. And so people have been working on, various math programming methods to solve this traveling salesperson problem. At least for, since Danzig and post-war.
Yeah, I suspect that the traveling salesperson problem, which that's a really great way to call it. I'm so used to it being called a more gender-specific kind of...
It traditionally would have been, and
Yeah.
I wanted to be a little more gender-neutral.
Yeah, absolutely. It's one of those ones where that's something that I try to be really mindful about, but that is the traveling salesperson problem is one place that I had not stamped that out.
Or we can just call it the TSP and avoid the issue altogether.
And yeah, with that problem, probably most of our listeners are aware of the problem, but we can quickly rehash it here, which is that it's that if you have a number of cities and you want to find the optimal route between those cities so that you spend, I guess, as little time and money cost, like
right.
your
some
classic
measure of
operations.
cost, whether it's distance or time, and you want to minimize that cost in terms of the order in which you visit those cities.
And when there's like 3 cities, it's computationally tractable, but then it very quickly, it's like, even I think with like 10 cities or something, it starts to become crazy, the number of possible paths between them. And so I know this is one of the places where I think there's been completely different kinds of computational approaches, like genetic algorithms.
Sure.
And I don't mean like a genetic machine learning algorithm. I mean literally like using biological material.
Right. I mean, the idea is that each solution is in and of itself like a genome, right? And so you sort of mix and match solutions to get new solutions And right, the idea would be that I'm going to, cut one good solution that I found with, and then add a piece of another good solution, so that right now and so essentially I'm reproducing and hopefully improving the fitness of my populations of solutions, and we sort of continue that, that reproduction to hopefully find the best solution.
And so that one is that you're describing a genetic machine learning algorithm there, right?
That's what's called a genetic algorithm.
But what I'm talking about is actually using like a liquid and having actual biological genetic material. And so I read about this years ago, but it's one of those like out there. It's because it's so computationally complex to try to model the traveling salesman perfectly with our computing methods that we use today predominantly. And there might be like quantum approaches to solving traveling salesman problem out there.
There could be, yeah.
But I remember reading years ago about using genetic information floating in solution, and I guess it must be similar to what you just described there, of genetic material. Kind of with genetic machine learning, you are using you're using different strains where you're like, okay, this strain was pretty good, that other strain was pretty good, let's mate them together and see what the result is. In this case, it's just random, I guess, where genetic, and I don't remember all the details, but the point is that it's such a computationally complex problem that people come up with really far out ideas for ways to try to solve it efficiently.
Right. Whether it's the genetic algorithm, either one of these, or ant colony algorithms and all these other things that have sort of emerged around different ways that we can, try to solve these more generally combinatorial optimization problems. And, but the TSP itself has been just the subject of just a tremendous amount of work, and whether it's sort of the heuristic solution methods that we're talking about, or more exact integer programming, coupled with various dynamic programming type of approaches, and those have those have evolved to the point, particularly through this Concord solver that is available, that can solve tours that have millions of cities in them.
Oh, really?
And solve them to exact solutions, right? Which is
this
really
Concord
impressive.
like the grape or like the jet?
I think it's spelled like the jet.
Right.
So I don't know the genesis of that name. I mean, maybe you have to have Bill Cook on your show and you can talk about it. I think he'd be a great interview.
And so this Concord solution, I mean, is there kind of like a high level way of describing that, or basically that's the point of this, is that the Concord, I can't remember now how we got into this. I interrupted you because you mentioned it briefly.
I was talking about the fact that the action space of the MDPs, when you get into these logistics problems, itself is combinatorial, because it's essentially the subproblem's a routing problem, and so you can't enumerate all these solutions, which becomes the problem.
Right. But the Concord solver can help you out.
Well, see, that becomes the challenge, in that, when you take something, when we use the neural net as sort of that approximation architecture, right? And if everybody's probably familiar with Q-learning, so I have a state of the world, right? That's everything I know about the world at this time. And so if you're thinking about a vehicle routing problem, it might be, the current location of my vehicles. We at least need to know, who the unserved customers are at that point. Maybe you want to hold on to some sort of route plan that maybe will change, right? This information can all be useful. Okay, so that's our state. And then from that state, we're at this point, we want to make a decision. And the challenge is that decision in and of itself can result in a routing problem. And when you think about, that's okay, right? If I have this neural net, I could pull that out, and maybe, I've used all linear activation functions. So I can, I now have a linear model, but doing that in a neural net, it could be incredibly large as a math program, making this training, then the training becomes almost impossible in and of itself. And that's And so, some of the things that people have done is instead of neural nets, let's just use some linear approximation of the future, right? And so now that's a little bit easier because I have this single kind of linear equation that goes in my objective, and I can solve that. And you can train those relatively quickly. But the truth is that that linear function is obviously it's a particular functional form, and that isn't necessarily the right form to get a good approximation of the future value of making of any particular decision, right? Which is why you want to use the neural net. And so you're at this sort of crossroads there with the, one really powerful technology in terms of its ability to approximate, but creating, on the other hand, then some really significant challenges in how we go about trying to solve the problem of essentially choosing the action in that case, right?
Mm-hmm. And so this sounds like we might be getting into cost function approximation. Is that which maybe we can put a pin in